Hello and welcome back to Calculus 1. Today we're going to work on definite integrals and then later on some of the rules of those integrals. Last time we talked about these concepts. We talked about the concept of area under the curve. And what I had there was an approximation for that area. We said that if we have any kind of a function, f of x, we can divide the area under the curve into these rectangles. Well, these are bad divisions. And then use either the right-hand side or the left-hand side. Let's use the right one to create rectangles, and then compute each area separately, because this point here will be x1, f of x1, so the height is the function computed at x1, and then each one of these points will have the same. So we were able to approximate the area by delta x, which was the width of each one of these, which is x1 minus x0 or x2 minus x1. Let me write. Delta x was b minus a over n, which is the number of rectangles. So we were able to compute this, let's say in this case, by f of x1 plus f of x2 plus f of x3 and plus f of x4, even though this one gives us 0. And we saw that all of this stuff that these regions that I am shading right now, that would be considered error. All of it is error. So how do we get it better? Well, we introduce more rectangles, and as you draw more rectangles, the amount of error decreases, because now the error would be the blue portion here. Considerably less error than before. So if I keep adding rectangles, there is less and less and less error. So as n, the number of rectangles, grows, the error gets smaller. Ultimately, if I send n to infinity, I will have exact area. So n going to infinity, having an infinite amount of rectangles, will result in the area. So now those of you who are really trying to understand integration and its application, this is the time to pay attention. Don't write anything, just stare at the screen, and then you'll have time to write it. Each rectangle is computed by function computed at some x. Let's call that xi, the ith value. I is a counter, 1, 2, 3, 4, times delta x. So each rectangle is computed with this. What I need to do is I need to add, and I'll explain this symbol. So this is summation symbol. I need to add all of these to infinity, but I'm not going to put infinity there. I'm going to put n up there, and I'm going to send that n to infinity. So the way this formula works is, we ignore this first. We say that the height times the width is the area of a single rectangle. Then you add all of the rectangles you have and then you say, let me have infinite amount of rectangles so the area is exact. So the formula actually works from backwards if you want to understand what's going on. So you've seen here 4 and then 8 rectangles. And you see how much less error you have. So all of these red shapes over here, shapes, all of these are actually now included in the true area once we use blue ones. More will be added to it if we use more rectangles and so on. So the more rectangles I use, the better precision. If I use infinitely many, we get exact. So one more time, height times the width is the area of a single rectangle. Add all of the rectangles you have, and then send the number of rectangles to infinity for the exact area. This is called the Riemann integral. It is the limit definition of the integral, and the integral would look like this. We know from differentials that this dx is equal to delta x, and in this case that's what it is. So this is why we are highly allergic when you forget and neglect writing dx, dt, and so on, because you are killing the concept. You are killing the concept of the integral. The integral is the area, and you have to have two things multiplying in order to have that area. Width times the height. And that dx is the width. So over here, you have the same thing. Function, which is the height, times the width, which is dx. And there is actually multiplication symbol in between, which we never write. So you can't just drop it because it doesn't do anything. It actually does. It's a half of the concept. All right? So this over here is known as Riemann integral. And this one computes, and we'll see why and how, area under the curve under certain circumstances. And we'll cover that later. What does it take to integrate, let's say, a function? So let's go like this. Find the area under a curve f of x equals 3x plus 2 on interval 3 to 5. It doesn't really matter. So just a quick sketch of this. It goes through 3 and then 3 to 5. So we are looking for the area of this trapezoid here. Clearly you can geometrically figure out what that area is because it's a trapezoid. You know the area for the trapezoid, average of two bases times the height. But we are actually going to use the Riemann integral to solve this. Now, you remember how we had limit definition of the derivative? The limit h goes to 0, f of x plus h minus f of x over h. You remember that from the last life? Yeah. So we used that, and then we learned the rules for differentiation. You memorized that derivative of sine is cosine and derivative of ln x is 1 over x, so that you don't have to do that limit procedure, which took half a page. Well, what I'm going to do now is the limit procedure for the integral. And the reason why you memorize the formulas in your previous 4.9 is to avoid what is going to happen now. So whatever you learn from those formulas, and then later on for U sub and whatever in Calc2, you better don't complain, because this is going to be alternative to it, all right, which is the way to actually do it. So how do we start this? We start by figuring out some of these rectangles. So x1, x2, x3, and so on. It starts at 3 and goes on. We compute delta x as 5 minus 3 over n, which is 2 over n. So I know that 2 over n is the delta x. Then, as I'm looking into this, I need this xi piece. So xi will be given by a plus I delta x. Does this mean? Well, remember that the first x1 is a, where you start. We start at 3. And then the next one, so that's the first piece. Remember, I is 1, 2, 3, 4, 5, right? I is the counter. So when I is equal to 0, then 0 times delta x is just a, which is where we start. When I is equal to 1, you have a and you're adding delta x, so that just jumps to the next position. And then when I is equal to 2, you're adding 2 delta x's, so then you are on this position, and then it goes like that. So in between every one of these, there is a delta x. These are not evenly spaced, so there is a delta x here, delta x, delta x, delta x, forever. So the first position is a. First position is a, and that's when I is equal to 0. So that zeroes out this piece. So the first x0 is a. And then, when I is equal to 1, you have a, which is the position, plus delta x, so you move here. When I is 2, you're there. 3, 4, 5, 6, 7. How many of those you get to use? So that is how we see, and that's actually the formula, the same like delta x formula. So delta x was b minus a over n. That was a formula. This is a formula as well. So now I can just apply that formula for our purpose. And I'll put I in the back. Now this I is not imaginary I, guys. This I is counter. It's not imaginary number. Don't confuse that stuff. So I is a simple counter. So what I have now is I have the value for delta x, and I have a value for xi. Now I need to find f of xi. Well, that's going to be my f of x with xi, and all I need to do is to plug in xi, which is 3 times 3 plus 2 over ni plus 2 solve this out. It's 9 plus 6 over ni plus 2, which is 11 plus 6 over ni. And finally, I have all of the ingredients to put all of this together. Now I'm going to write on the board the formula one more time so you can look at both things at the same time. Limit n goes to infinity, summation I to n of f of xi times delta x. I have an expression for this now. I replace it. And I have expression for this, which is 2 over n. I replace that as well. So the whole thing now looks like, so plug all of those in. We get limit, n goes to infinity, summation I to n of 11 plus 6 over ni times 2 over n. And now we have to solve this expression. Solving this involves the formulas that are given in the textbook, but first we are going to distribute this 22 over n plus 12 over n squared I. The limit stays, which is now limit applies over the summation I n of 22 over n plus summation I to n of 12 over n squared I. Now, the rules of summations are also something that you haven't dealt with before. The variable for summation is I, not n or x or anything like that. So you get to kick 1 over n in front and just have 22. On the second summation, you kick 1 over n squared out, and you are left with a summation of 12i. Bear with me another 10 lines and we're done. Now the formula for this and this. Formula for this one, the first one is 22n. There is a formula, well, I'll write them later so I don't ruin the continuity here. Plus 1 over n squared times 12 times, and the formula for this one is n plus 1 divided by 2. And now you're finally back in chapter 2 when you're taking basic derivatives. Sorry, limits. So what do you have? These guys cancel. You have 22 plus these guys cancel, and one of the n's cancel. 6n plus 1 over n. So it should give you 22 plus 6, which is 28. That's the area. So who's glad that you're not in the honors section that have to do this on the test? 2 students only? So should we put this on the test though? Yeah. So you saw the procedure. All right, now let's see what is the shorthand of doing this. The same problem of figuring out the area for f of x equals to, what was it? On 3 to 5? Yeah. Is this. You find the integral 3 to 5 for 3x plus 2 dx. The integral is 3x over 2 plus 2x. And you put this vertical line which says computed at 3 to 5. You compute this at the upper limit first. And then you subtract the lower limit. And you will eventually get 28. So I don't think we have to do it like when you go for the I exam, which one's better, A or B, you know. 25, 75, and then minus 27 over 2, they cancel, and then you do figure out. It's going to be 28. It should be. If anyone is computing this. It is? Okay, it is. Okay. What you see in front of you right now on the screen is called the definite integral. Definite integral under certain circumstances computes area under the curve. Now I'm going to write the formula which is hidden in here. The way you compute this integral is you find the antiderivative, 4.9, and then you compute that integral 3 to 5, which is f of b minus f of a and b. Right? So f of b minus f of a. Where is your grade going down? You forget these parentheses, and then this sign doesn't get changed, and then the whole thing goes to hell. So, f of b minus f of a, but when you are plugging stuff in, make sure you have the parentheses there, because this minus will distribute to each term. The more steps you skip, the more mistakes you're going to make along the way, because you don't have the, what's it called? Experience in computing this quickly. It's always going to be 4 steps, right? To compute, to write out, and then to compute again. I mean 3 steps, not 4 steps. So let's write the formula. Integral of f of x dx from a to b is antiderivative computed from a to b, which is f of b minus f of a. So let's practice one, and then we're going to take a look at the properties of these. Well, let's practice 2, because you can. First one, here's problem 16. Integral 0 to 4 of 8 minus 2x squared dx. Guys, note that I'm using parentheses here because I have 2 terms. Dx needs to multiply both of them. Right? This is the height, this is the width. So you need, if you have multiple terms, you have to put parentheses for correct mathematical notation. You know 4.9. It was on your exam. Use 4.9 to find the antiderivatives of 8 and 2x squared, and then compute whatever you get at 0, well, at 4 first, and then subtract, compute it at 0. And then you apply the formula. You plug in the Let's take a look at this together. So we have 8x minus 2x over 3 over 3, so 2x cubed over 3, computed from 0 to 4. We are going to plug in 4 first. And then subtract 0. All of these will go to 0. That doesn't happen all the time, guys. What's cosine of 0? 1. What's e to the 0? So don't play with fire to immediately dismiss calculation if you see 0. Sometimes it's not going to give you 0. For polynomials, sure, they all go to 0. But cosine of 0 is 1, e to the 0 is 1, some other stuff also. So make sure that you are carefully computing this. 8 times 4 is 32, minus 32 over 3. So, oh, it's supposed to be cubed? Oh, cubed. All right. So in that case, it's 64. Times 3 for common denominator would be 96 minus 64 over 3 gives us 32 over 3. What is this? This is area under the curve from 0 to 4. If I am to graph this function and say it looks like this, so let's say 0 to 4, it would be area here. That's what we just did. One more example. That's exact area. That's exact area under the curve. Oh, there is a times 2 over here. That's 128. 128. So what do I get? Then that's not the area under the curve. I have to erase that part. It's not the area under the curve. What do I get? Negative 32. All right. It's the value of the definite integral. I did one right and then I did one wrong. Keep a tally. Start slowly. Start the day off like that. Yes. Yes, but also next lecture 5.3. So we'll do one more example, properties of this, and the next lecture will explain that. When we talk about fundamental theorem of calculus, we'll understand the difference between the antiderivatives computed as a definite integral and the area under the curve, when are they the same thing and when they are not. And I usually have a problem on the final that addresses that if you understood it and learned that or not. But that's next section. So just negative 32 over 3, and let's do one more. What would you like? Something nice. Here. Compute this one. So what do you all have? 0. Is area under the cosine graph 0? The answer is hell no, right? We know it's not because you can actually color it, right? If you can color it, it means it has area. So we are going to learn in 5.3 the difference between definite integrals in general and definite integrals that actually compute area under the curve. And you will be able to quickly distinguish between the two and then use the... So you have to be careful what the problem says. If the problem says compute the integral, your answer is 0. But if it says find the area under the cosine curve, answer is not 0. And we're going to compute that exact value in 5.3. So let's just do this one and then switch to 5.3. So properties after this. What's a cosine, integral of cosine? Sine. So we have sine x computed from 0 to 2 pi, and then we have sine of 2 pi minus sine of 0. We get 0 minus 0, which is 0. And we know, is this still going? Yeah. And we know that the value of the integral is 0, and we now kind of sense that there's something there with the issue with the area. We'll figure it out. Let's talk about the properties of definite integrals. These properties are important because eventually you are going to run into them and they can save you some quality computing time. One of them is that if the limits are in the wrong order, which means larger number on the bottom and a higher number on top, they can be swapped. So integral from a to b of f of x dx is negative integral b to a f of x dx. So if you put the bottom limit up and from up below, you put the minus sign in front. The proof for this is extremely easy because it just involves the f of b minus f of a and then the negative sign in front. So those of you a little bit more inclined to proving stuff, this proof takes literally 5 seconds. This one is f of b minus f of a. This one is f of a minus f of b, but then there is a minus in front of everything, and when you distribute, you see that they are the same. So that's that property. It is useful. It is going to be useful for the first time in its full light in 5.5, next class. Because sometimes when you do the u substitution, when you transform limits, you will end up with a larger number in the lower limit and a smaller number in the upper limit, and then you have to swap them. You don't have to swap them, but we swap them. And that's when the minus pops up in front of the integral. Number 2, if you go from the same, between the two same numbers, the integral value must be 0. Guys, your delta x, which is your width, is 0. Because remember what delta x is. dx is delta x, which is b minus a over n, right? Well, if b is also a minus a is 0. So all of the widths are 0. And when you multiply height times the width, and width is always a 0, all of the rectangles are 0. Also, another way to understand this is draw a graph where you are going between a and b, but then a and b are the same value, so there is no width to it at all. You can also graphically prove this one. Observe that both limits are the same value. That's an A. Okay. All of the properties that you learned in your 4.9 still hold. If you are integrating addition or subtraction of two functions, they are still the sum or difference of them individually. This is the one where we technically almost never use, but you might be. The same thing for the constant. You can kick constant outside if you need to do it for whatever reason. And now, the most useful one which we have to use in the next section. And that is, I don't know how to make it special. I already used red. Purple? What happened? I can't hear you. This on the air conditioning. What did you say? Guys, for the integral, if you carefully observe, let's say, area A to B, and you pick some C, I don't want to be right in the middle, here. You pick C anywhere in between. It should be common sense, looking at it, that area 1 and area 2 together make overall area. So this means that I can take integral A to B and break it over two integrals with the value C, and that value C can be anywhere as long as this function is continuous, nicely behaved, and all that kind of stuff. So A to C of the same f of x dx plus C to B f of x dx. So there is this continuity through C, right? It's still A to B, right? You can easily prove this as well, because this would be capital F of C minus F of A, and then you will have F of C minus F of B, and then these two would cancel. This is crucial for the next section where we discuss area between two, the difference between computing the integral and computing the area. This one, it must be clear how it's used. So you are allowed to break this interval anywhere. Anywhere. Pick a value C between A and B. And you can do that actually as many times as you have to. 10 times. Doesn't matter. You can break any number of times. But wherever you end, you have to start there the next integral. And then go on. This one is also going to be used later on for improper integrals in Calculus 2. So you must know this rule. The other ones are kind of convenience rules, but this one is a must. All right. That ends 5.2. I will restart the stream for 5.3.